Beneath the vast expanse of the Pacific Ocean lies a restless giant, the Pacific Plate, covering more than a third of Earth's surface. It is the single largest tectonic plate on the planet, bigger than all of North America and Eurasia combined. For decades, geologists considered it a stable, unbreakable slab of rock, sliding steadily across the mantle and shaping the Pacific Ring of Fire with its collisions. But what if this colossal plate isn't as solid as we thought? What if deep beneath the waves, the very foundation of the Pacific Ocean is beginning to crack? Recent seismic studies and ocean floor surveys are revealing a startling reality. The Pacific Plate, once seen as Earth's most resilient slab of crust, may be fracturing under the immense stresses of its size and speed. Earthquakes rumbling in unexpected places, hotspots punching holes through its surface, and the rise of mysterious microplates all point to a plate under strain. If this giant is truly splintering, the consequences could ripple across the globe, reshaping coastlines, awakening dormant volcanoes, and triggering earthquakes of unprecedented power. The Pacific Plate is cracking, and humanity may be standing on the edge of one of geology's most profound transformations. Before we dive further into this topic, please take a second to click on that subscribe button and like this video, as it's the best way to support this channel. The Pacific Plate dominates Earth's surface, covering about 1/3 of the planet's crust. Unlike continental plates that carry land masses, much of the Pacific Plate is composed of dense oceanic lithosphere, which is thinner yet heavier than continental crust. It is bordered by nearly every type of plate boundary, subduction zones, transform faults, and spreading ridges, making it the central engine of Earth's most dramatic tectonic activity. To its east, it plunges beneath North and South America at the Peruchili Trench and Aleutian Trench. To the west, it collides with the complex Philippine, Sea Plate, and Eurasian Plate, creating vast volcanic arcs. To the south, it interacts with the Indo-Australian Plate along the Tomography subduction zone. Its northern boundary includes the famously dangerous San Andreas Fault in California, where it slides past the North American Plate. This constant motion is powered by mantle convection, the slow circulation of heat and material within Earth's interior. The Pacific Plate migrates northwest at roughly 7 to 11 centimeters per year, one of the fastest rates of any tectonic plate. Over millions of years, this relentless drift has shaped the Pacific Ocean basin, produced island chains like Hawaii, and helped form the fiery ring of fire that girdles the ocean with volcanoes and earthquakes. For most of the 20th century, the theory of plate tectonics treated plates as coherent blocks, solid enough to transmit stresses over thousands of kilometers without breaking. But as seismology and satellite geodesy advanced, researchers began to notice anomalies. Some earthquakes were occurring, not along well-known subduction zones or transform faults, but in the middle of the Pacific Plate itself. Small but measurable deformations were being detected across what should have been stable regions. These findings hinted at a more complex reality. The Pacific Plate, vast though it is, may be crisscrossed with hidden fractures. Some are relics of ancient rifts where the plate originally formed at mid-ocean ridges. Others appear to be new cracks responding to stresses generated by the plate's enormous size and speed. Ocean floor mapping has revealed new fault systems slicing through its interior, and in some regions, microplatesmolar fragments of lithosphere have begun to peel away from the main mass. The strongest evidence for the Pacific Plate's internal cracking comes from earthquakes. Typically, the most destructive quakes cluster around subduction zones where plates grind together. Yet seismic networks have recorded intraplet earthquakes, tremors originating far from boundaries within the Pacific Plate. These events are usually moderate in magnitude, but their occurrence is striking. For instance, the central Pacific near Hawaii has experienced swarms of small quakes that do not neatly align with plate edges. Some scientists believe these tremors indicate the plate bending, flexing, and fracturing as it rides over mantle hotspots. Other intraplet earthquakes have been linked to stresses from subduction zones, transmitting deep into the plate's interior. The very fact that quakes can propagate within what was assumed to be a rigid block suggests that the Pacific Plate is riddled with zones of weakness. Volcanism provides another window into the plate's instability. The Hawaiian Emperor Seamount chain, stretching thousands of kilometers across the Pacific, records the Pacific Plate's slow journey over a stationary hotspot in the mantle. Each island is a time marker formed as magma punched through the plate and built massive shield volcanoes. But the hotspot story also reveals something more. The Pacific Plate is not immune to piercing and cracking from below. As it drifts, magma from the hotspot repeatedly fractures the lithosphere, creating new volcanic islands. The bend in the Hawaiian Emperor chain, which occurred about 47 million years ago, shows how dramatic shifts in plate motion can redirect stress and fracture the crust in new directions. Similar hotspots, like those beneath Samoa and Tahiti, exploit weaknesses in the Pacific Plate and further contribute to its fragmentation. One of the most striking signs of the Pacific Plate's instability is the presence of microplates in the South Pacific. Between the Pacific and Indo-Australian boundaries lies several smaller plates, such as the Easter, Juan Fernandez, and Niuafo'ou plates. These fragments were once considered anomalies, but geophysical evidence shows they are products of the Pacific Plate itself breaking apart. In some regions, spreading ridges and transform faults intersect in complicated ways, creating triple junctions where new microplates can form. As the Pacific Plate continues to move rapidly, stresses accumulate at these junctions, eventually cracking the lithosphere into smaller pieces. Over geological timescales, such microplates may grow more prominent, accelerating the fragmentation of the once monolithic Pacific Plate. To understand the Pacific Plate's potential fate, it helps to look at history. Tens of millions of years ago, another massive oceanic plate, the Farallon Plate, dominated the eastern Pacific. Over time, subduction consumed most of the Farallon beneath North America and South America. The remnants survive today as the Cocos Plate, Nazca Plate, and Juan de Fuca Plate. What was once a giant coherent plate fragmented into smaller pieces due to relentless tectonic forces. The Pacific Plate may be undergoing a similar process, though it is far larger and more resilient than the Farallon was. The cracks and microplates emerging suggest that no plate, no matter how vast, is immune to Earth's constant reshaping. If the Pacific Plate were to break into several large fragments, the tectonic map of the planet would be redrawn with profound consequences for seismic risk, volcanism, and continental drift. The Pacific Plate's instability is not just an academic issue. More than 800 million people live along the Ring of Fire, where the Pacific Plate collide with others. This belt includes Japan, the Philippines, Indonesia, New Zealand, Chile, and the west coast of North America and Central America. These regions already experience frequent earthquakes and volcanic eruptions due to subduction processes. If the Pacific Plate is cracking internally, it could alter the distribution of stress along its boundaries. Subduction zones might experience sudden shifts in strain, potentially triggering larger earthquakes. Volcanic arcs could be reactivated or intensified. Intraplet fractures might produce unexpected seismic hazards in places thought to be relatively safe. Any major reorganization of stresses within the Pacific Plate would ripple outward to these population centers, magnifying the risk of catastrophic disasters. What might the future hold for the Pacific Plate? Some geologists envision it eventually splitting into two or more massive plates, perhaps along existing fracture zones in the South Pacific. Others argue that it may gradually shrink as subduction consumes it from its margins, leaving only remnants like the Farallon before it. In the most extreme scenarios, internal cracking could lead to the creation of new spreading centers within the plate, birthing entirely new ocean basins. Such processes would unfold over tens of millions of years, but their beginnings may already be visible in the microplates and fractures of today. From a human perspective, the concern is not the distant future, but the near-term consequences. If the Pacific Plate is redistributing stress, it could make certain subduction zones more prone to large earthquakes in the coming centuries. Scientists are particularly watchful of regions like the Cascadia subduction zone of the Pacific Northwest, the Nankai Trough in Japan, and the Chilean Trenchal capable of producing magnitude 9 megathrust earthquakes. The Pacific Plate's future is one of both scientific intrigue and global consequence. If the fractures currently forming within its vast expanse continue to grow, they could mark the beginning of a long process of fragmentation, much like the ancient Farallon Plate that once dominated the Pacific before splintering into smaller plates millions of years ago. While such transformations unfold over geological timescales, their early signs, microplates peeling away, intraplet earthquakes, and hotspot-driven cracks suggest that the Pacific Plate may be entering a new evolutionary stage. In the near term, this cracking could alter how stresses are distributed along the Ring of Fire, increasing the potential for powerful earthquakes and volcanic eruptions in regions already prone to disaster. Over the next several million years, the Pacific Plate itself may split into separate tectonic entities, reshaping ocean basins and even influencing continental drift. For humanity, the Pacific Plate's instability is both a warning and an opportunity, a reminder that Earth's surface is never static, and a challenge to advance scientific monitoring so we can better anticipate the planet's next great shifts.